I'd like to introduce our next speaker, PhD candidate Chloe Gentgen. Chloe is in the Engineering Systems Lab in the Department of Aeronautics and Astronautics. And she has a talk about her research. And I'd like to welcome Chloe and give the floor to you. There you go.
Thank you so much, George. Does this sound OK? All right. So thank you for the introduction. I'm really happy to be here today with all of you. I'm a PhD student studying planetary science mission, and in particular, the formulation of new planetary science mission. I look at how to make missions more robust and adaptable to uncertainty, and also how can we integrate new technologies into these missions. And so today, my talk's actually going to nail down on something very specific. Could we use Starship for a mission to Uranus? So it's a bit far away from the Earth to Moon theme, but I think this might be your only outer solar system talk of the day, so bear with me. All right, let's get going. Oh, before I start, so this work comes from a collaboration with my lab mate Daniel Gackenauer and my professor Ollie de Weck. It comes from a paper that was presented at IEEE Aerospace last month, which is not yet published, so it's a little sneak peek. All right, so let's take a step back. This is NASA's planetary science fleet, current and future missions. And when we think about planetary science mission, there's a typical sequence we usually follow. First, you do a flyby, which gives you a very brief overview of the system. Then you have an orbiter, where you spend years in the specific system you're interested in. Then eventually, you try to land. You try to do some surface exploration. And at the end of the day, you bring back samples. Then the next step is like crewed missions. And so if we look at this chart, we can see that for the Moon and Mars, we've had a lot of missions. Obviously, we've brought back samples from the Moon, and we're hoping to bring back samples from Mars. The outer solar system is a bit more empty in missions, and especially these days, the two planets that we see, Uranus and Neptune, seem a little lonely. And so today I want to talk about why we should go explore what are called these ice giants and an innovative way to think about it. All right, so why explore Uranus? Well, first of all, we've just never been for more than 48 hours. This seems crazy. Voyager flew by Uranus in 1986. And since then, we've only had remote observations of the planet. Our last big planetary orbiter mission was Cassini in 1997. So since then, we haven't done any new dedicated mission to a whole planet. And discovering a planet is so interesting. You're going to learn about the interior, potentially its atmosphere, the moon's ring, magnetosphere. There's really a lot for all the different scientists. Uranus is a weird planet. It's tilted. It's cold. We don't really understand why it rotates on its side. Its formation is very unclear. And we don't understand its interior. And more recently, actually, this aspect of formation of Uranus has drawn a lot of attention because we've realized that Uranus and Neptune are what are most similar to the exoplanets we're discovering. So if we want to understand exoplanets, potential life outside of the solar system, we need to understand more about these ice giants. And finally, again, a somewhat recent interest in ocean worlds could also be applied to Uranus. And so we think that some of its moons could be ocean worlds. So these have all been a long time coming. I've been talking about it. But there's a real interest in going now. There's an opportunity to launch a mission and arrive around Uranus's equinox. So let me explain this a little bit. Because Uranus is rotating on its side, its configuration is very different throughout its orbit around the sun. It has solstice, which is when Voyager last came, and then you have the equinox period. And an orbit of Uranus is about 84 years. So really, you only have opportunities to explore Uranus at equinox every 40 years. And an opportunity is coming up now. All right, so this seems really exciting. Why haven't we been? It's really all about distances. Uranus is very, very far away. So if you think about Jupiter, which already seems kind of far, it's about 5 AU from the sun. Saturn, nearly the double. Uranus, double it again. And so really we're at 19 astronomical units from the sun. We're not even going to talk about Neptune today that's at 30 AU, making it even more complicated when we're talking about an orbital mission that has to arrive at these destinations. And so let's dig a little deeper into these challenges. What are the challenges related to exploring at 19 AU? Well, the first one is about this launch energy. We need a lot of energy to arrive to these destinations. And this is also going to limit our delivered mass, because it's very different to do an orbiter mission than to do a flyby. For an orbiter mission, you actually need to slow down at destination and enter into orbit. So if your energy is really high, you're going to have to do, presumably, a very large burn at destination and use a lot of your propellant for that, limiting your payload mass. I've mentioned that with such distances, the times of flights to reach the destination are going to be huge. We're talking roughly 10 to 15 years. And something you might not consider, but that's really challenging when designing these missions, is that in the 13 to 15 years of cruise, it's challenging to keep the expertise of the mission team that designed the instruments, the spacecraft, and of the scientists. And the reason this time of flight is so long is that we'd have to do gravity assists to build up the energy needed. The last issue is the power generation issue. At 19 AU, it's way too far to leverage solar power. Solar power decreases with 1 R squared. So it's really not an option anymore. And so we're looking at nuclear reactors, so radioisotope thermoelectric generators. These rely on plutonium-238. And unfortunately, the United States has stopped production of this plutonium since the late 1980s. And so really here we're starting to understand why it's been so challenging and why we haven't been to Uranus yet. But the times are changing a little, and there are opportunities today. We have some super heavy launch vehicles that are available, so I'm thinking about Falcon Heavy, even if it's in its expendable version, and there could even be some future in-development launch vehicles. We have a prime opportunity for a Jupiter flyby if we're able to launch in 2031, 2032. And in the roughly 2010s, we've restarted production of plutonium. So the supplies are just very limited, but we see a window of opportunity here. And so understandably, Uranus has been selected by the latest decadal survey as the highest priority flagship, so that's NASA's big missions for the decade. They identified a concept called Uranus Orbiter and Probe. So it's an orbiter that also includes an atmospheric probe that's going to enter the atmosphere. And the orbiter is going to study the interior of the planet, the moons, and the magnetosphere. It's going to launch on a Falcon Heavy expandable. And it's going to launch in 2031, do a Jupiter flyby in 2035, and then arrive at Uranus after a 13.4-year cruise in 2044. So this is what was proposed in the decadal survey, which came out in 2022. Unfortunately, it seems likely that launch would be postponed. So even without talking about changes that could be related to the new administration, which are way too soon to say, the latest presidential budget was assuming a start of funding for this mission no earlier than 2027, when this concept required start of funding in 2024. So we're going to have a launch postponed compared to this concept. And the big issue here is that we might have a Jupiter flyby become unavailable. So what can we do? Well, it demands to look at alternative options. But the longer time before the mission launch is also an opportunity to look at more innovative technologies. So let's look at our option today. The first option would be the option that has the most similar architecture to the proposed concept. It would launch after 2031, 2032. That's a new window we're looking at. And it would include what we call an inner tour of the solar system. So it would launch on a Falcon Heavy expendable as well. But to replace this Jupiter flyby, it would do a Venus flyby, and also actually Earth flyby that I'm not showing in the slide. Compared to the baseline, it would offer a lower mass at Uranus and a roughly similar time of flight. However, there are thermal challenges associated with doing flybys in the inner solar system, so that has to be taken into account. Some of a bit more exotic option could be solar electric stages. We've done solar electric stages before, but there's this idea that it's inherently complex. So for some reason, planetary science community doesn't love this idea. But it could be a valuable option, bringing us a similar mass than the baseline mission, a bit of a shorter time of flight. As I mentioned, there is this increased complexity. And then we can look at even further innovative concepts. We have this idea of doing aero capture, which I'll talk a little bit more later. But with a Falcon Heavy expandable and a heritage entry vehicle such as the Mars Science Laboratory capsule, in addition to a Jupiter flyby, we can have a similar mass and a much shorter time of flight, 8 years to Uranus. That's really exciting. However, we have never done air capture. The technology readiness might be a little tricky here. Some options include doing SLS with an extra kick stage. And so this configuration would also enable you to do a Jupiter flyby. Could have a similar mass, 10-year time of flight. The question here comes about vehicle availability and whether we will be able to have an SLS available for planetary science mission. So there's a lot of studies in the literature looking at these, but today our focus is going to be on Starship. And there's surprisingly not a lot of studies looking into that. So our question here is Starship a feasible and valuable launch option for a Uranus flagship mission? All right, a little bit of intro of the vehicle that you all know. Starship is a vehicle currently designed by SpaceX. It's under development. It's what we call the super heavy launch vehicle. It aims to launch 150 tons to LEO. Its key characteristics is that it's fully reusable, but also refuelable in orbit. And this comes from the fact that Starship was not only thought and designed for payload delivery, but also for crewed missions to Mars. And actually, because it was designed for crewed mission to Mars, it was selected as part of the NASA Artemis campaign as an option for a human landing system on the moon. All right, but what about Starship for science, like NASA science mission, robotic exploration? Well, there's been studies on how Starship could support payloads for the moon, Mars. There's also been a big study about how it could be really helpful to bring large telescopes to LEO or Lagrange points. There's really not been a lot of studies for the outer solar system. What's really interesting and that you can fairly quickly realize is that you could go to Uranus without any flybys if you refuel Starship. So that's what we're going to look into, and we're going to look into the numbers a little. All right, so for a study, the first big step, figuring out which design parameters we would pick. These are the design parameters that we need in order to perform our study. It's complicated. It wasn't an easy task. Starship is in development. There are multiple versions, a lot of iterations, and not all the information is publicly available. So we had to look here and there for signs and try to construct a feasible and what we thought was reasonable set of numbers for our study. So these are the numbers we selected. They're the most similar to the Flight 3 version that flew last year. We're considering a payload mass to LEO of 150 tons, a dry mass for the vehicle of 100 tons, a propellant capacity of 1,200, and then we're considering that during each refueling trip, you can transfer 80% of your propellants. So we're assuming some boil-off, ullage, and potentially that a depot could limit the fuel. All right, so now it's very interesting. We have this vehicle that we can refuel in orbit. By refueling it in orbit, we can kind of reset the rocket equation. And so it really makes us think about our capacity in terms of specific energy to the outer solar system very differently. And so we can create this chart where we see on the x-axis the delta V and the y-axis the payload mass. And every line here is what's feasible with the number of refueling trips. So we can see that fully refueled, so with 10 refueling trips, Starship could have as much as 9.5, roughly, kilometers per second. And we can also see that these lines seem very vertical. It's very easy to have hundreds of tons with such high delta Vs. So now we're going to look at, OK, what does this mean in terms of trajectories? We're looking at direct trajectories from Earth to Uranus. So we're using Lambert solvers. We're looking at a circular initial orbit for Starship, which is an assumption we took for a paper, but is actually highly debatable. It is very likely that Starship would decide to launch for interplanetary missions from a highly elliptical orbit and would refuel in this orbit, but this was a simplification we took. And then at Uranus, we have our science parking orbit, which is a highly elliptical orbit that's been selected for various missions. What we see very quickly when we draw our park shop plots and our different analysis is that we have launch windows that repeat every year. And from a programmatic standpoint, that's very interesting, and I'll talk a bit more later. Here, what we can do is taking all the information, and for a given time of flight, we can identify what's the minimum delta V that would enable a mission with this time of flight. And so I said that Starship had about a bit more than 9 kilometers per second. That means this black line over here. And if you look, you see that we have our departure delta V line here, arrival delta V line here if you were to do delta V arrival with Starship, and then total. So what's interesting that we see in this area is that actually you could do with Starship the departure burn, keep Starship all the way to Uranus, and then do your arrival burn with Starship too. Our studies show that it's less effective than doing your departure burn with Starship, jettisoning it, and then doing your arrival burn with the spacecraft. But it's still an interesting result to show you the capabilities of this vehicle. All right, so let's look a little bit at the numbers. What mass, what times of flight are we looking at? And so we created these plots where we have the time of flight in years on the x-axis, then the payload mass. And this is, for reference, the Uranus Orbiter and Probe reference mission. It brings about 4 tons into orbit at Uranus for a 13.4-year mission. Cruise time, sorry. So this is our analysis. These different numbers and colors correspond to different number of refueling trips. And so very quickly, we can see that we can outperform the baseline mission. Let's look at a few numbers. The maximum inserted payload mass could be 48 tons at Uranus. That's 12 times what the current mission is doing. I said that we were doing the arrival burn with the spacecraft. There is a practical limit with the delta V that a spacecraft could do at destination in terms of its design, but also in terms of managing the burn. And so we set this limit at 2 kilometers per second. So we're only looking at the right part of the chart. This still means that we could have a time of flight of 8.4 years with a payload up to 25 tons. That's, again, very consequent. But there's also something very interesting that we realized you could do with Starship. You could use Starship to perform aerocapture at Uranus. So let's take a step back here. What's aerocapture? Aerocapture is when you use aerodynamic drag to capture within a planet with minimal fuel burn. This is what it looks like. You need a body with an atmosphere. You have your hyperbolic approach. You enter your atmosphere. You exit it with a lower energy. And then you do a small periapse raise maneuver, and you're in orbit. And so Starship, because of its design, has an inherent higher L/D ratio. And so we're able to analyze how the different configurations with the fins, deflected or not, are able to perform in this aerocapture study. And what we've shown is that the heating and deceleration rates are actually very comparable to other Uranus aerocapture studies. But as I mentioned at the beginning, there are quite a few because it's a very interesting option, even with a Falcon Heavy as a launch vehicle. So what we've shown here is that aerocapture with Starship is likely possible at Uranus, which is a new result and very exciting one. And so we can create these plots again for that scenario. The plots are even better, right? So we have up to 55 tons inserted in orbit and a shorter time of flight of 5.5 years. That's nearly 3 times shorter than what we're currently considering otherwise. I do want to mention that there are some inherent challenges with that. And without even mentioning the side that aerocapture is yet to be proven, in this scenario, you have to bring your Starship vehicle all the way to Uranus. And so then there's questions about, well, how are you going to power the Starship vehicle during cruise? How are you going to manage its thermal constraints? You also need to adapt the thermal protection sizing. It's not going to be the same as a Starship for Mars or Earth, so that requires extra analysis that we haven't done yet. All right, so we have larger masses, shorter time of flights. What do we want to do? Well, the first option is let's use this higher mass, right? Let's have additional instruments, additional probes, potentially even a smaller spacecraft. Or we could just bring, and something to note here is that with a Starship architecture, we're not as much limited by mass, but now we're limited by power. So I mentioned at the beginning the limited supplies of RTGs. This is actually still a concern for a Uranus mission. There's a debate and an uncertainty about whether we would have 2 or 3 RTGs. And although the baseline mission showed that it was probably feasible with 2 RTGs, it starts to become impossible to think of enhancement to the mission if you have only 2. If you have 3 RTGs, we've actually shown that you could bring 2 spacecrafts to Uranus. You could bring a large spacecraft that would do your equatorial tour and study all the moons and rings. And then you could have a highly inclination, smaller spacecraft that would look at your interior and your magnetosphere. I think there's something wrong with the slide, but that's fine. Adding extra instruments, extra spacecraft will necessarily result in higher costs and increased complexity. So that's not necessarily the way to do it. We mentioned at the beginning that we started looking at this Starship question because we wanted to arrive earlier. So let's look at an architecture that focuses this shorter time of flight. And let's see actually what would happen if we took the exact same spacecraft that NASA has already been working and proposing and just trying to launch it faster. If the spacecraft does the insertion burn, if it actually does the very same delta V burn that what's currently proposed, we could arrive at Uranus in 11 years. So that's about 2.5 years faster. But if you can do a bigger burn, if you can do a 2 kilometers per second burn at destination, you can arrive at 8.5 years. As I mentioned, with AeroCapture, it gets even shorter. What's really interesting to understand here is that I mentioned how a short time of flight is good because then your team you're not losing your team as much over the years. You also get a longer science phase if your cruise is shorter. Let me explain. We're using the RTGs to power our spacecraft, and these have their power output decay year by year. And so roughly, usually, we say that they have an 18-year lifetime. And obviously, they still have power after that, but it's decreasing and decreasing. If you have a 13-year cruise, you have 5 years of science operation. If you have an 8-year cruise, you can have a 10-year science operation. Now, I'm not saying that we should do that, but it's very interesting, specifically when we're exploring a whole system where we need to do plane change, and we need to look really close at the body and then really far, and be in an inclined plane at some point and equatorial. That's really an interesting result. All right, so let's talk a little bit programmatically, and more particularly schedule. We wanted to arrive faster. So what could it look like? Again, not taking most recent administration change in mind, the latest information we had was that we could have a funding start in 2027. That means phase A start in planetary science mission. Typically, 2 years after that, you have launch vehicle selection. That would be in 2029. Something I mentioned earlier is that Starship has been selected with its human landing system variant for the Artemis campaign. In particular, it's supposed to land on the moon with Artemis 3. And to land on the moon, it must have demonstrated in-orbit refueling before. And so what we're assuming here is that most likely, by the time we need to pick the vehicle, we would have known whether Starship has managed its bets and is able to do in-orbit refueling or not. Then we have the roughly 7 to 8 year of mission development. That's typical for these large missions. And so you arrive in the launch window between 2035 and 2040. Then with a 6 to 11 year time of flight, you're able to arrive around equinox, which was our key goal here. And so this is really an interesting result. And it all comes down to the fact that we don't have to make a crazy bet, right? We just have to consider that Starship is an option. And by the time we need to make the decision, we will mostly have all the elements in hand. We've also done some analysis on more technical risk. We've also done a cost analysis. But in the interest of time, I'm going to skip it today. But if you're interested, please come and chat with me. And all right, so let's come to our conclusions. Missions to Uranus could truly transform our understanding of ice giants, but also exoplanets, and even astrobiology. Starship enables a direct transfer to Uranus if refueling is available. It delivers more mass and in shorter times of flight than current architectures, and it also improves launch flexibility and chances of arriving before equinox. There are a lot of key technical and programmatic risks that still need to be addressed, but it's still an exciting opportunity that should be studied. And so thank you so much for your time, and don't hesitate to reach out.